contractor, certified landscape irrigation auditor. Been teaching for the IA for almost 15 years now, as well as a past member of the board of directors for the Irrigation Association of New Jersey. So I've kind of chewed a lot of dirt on all sides of the irrigation sector. It's a really exciting time to be in agricultural irrigation because we're seeing what we're going to talk about today happened many years ago in the turf sector. So this is some pretty exciting opportunities. We're going to be talking about new control technologies. Center pivots haven't really significantly changed in the last 50 years. When you see a center pivot out there in the field, it looks all virtually identical to what you would have seen 30, 40, 50 years ago, which leads people to think, well, really they're not changing that much, and that's not true. What we've seen is that modern irrigation with that existing structure, it's no longer about just watering efficiency, but being able to monitor what that equipment is doing, being able to remotely control that equipment, as well as get some value-added information and provide some value-added services to the managers of that piece of equipment. So the innovations that we've seen happen in the last few years in center pivot technology have been in the control portion. And we're going to be talking about the different ways that that occurs today. So what's our agenda? We're going to start out talking about PCs, computers, programmable logic controllers, where those are used on center pivot machines, how they're beneficial to a grower. Then we're going to start talking about GPS monitoring, GPS guidance, what we can do with the global positioning system, and how that can enhance your efficacy when it comes to irrigation. We're going to be talking about telemetry. This has been a huge leap in the irrigation industry when it comes to remote monitoring, remote control, remote data reporting, and things like that. Then we're going to bleed right into that remote monitoring and control. How can you guys get data from your equipment without having to be on site? How can you manage more pieces of equipment while you're not on site? And finally, we're going to finish up with a concept called variable rate irrigation. Thank you very much. We're going to finish up with a concept called variable rate irrigation, which is one of the newest technologies in center pivots, and that allows us to actually spot apply water in the field based on crop conditions, soil type, things like that. This has been an emerging technology for the last couple of years. It's been in research at Clemson and other places, and we've perfected it to the point that we can begin to introduce those concepts to the growers and allow them to bring that in. So we're going to explore some of the terminology behind that, how that works, and what it does. So the first thing that we were going to talk about was PCs, computers, programmable logic controllers. We're starting to see these appear in center pivots. Well, where do you put a computer on a center pivot? Well, we've got several different locations where we're using this type of technology, what's called the single board computer, or the SBC, as well as a programmable logic controller. We see it in the main control panels. This is a sample of what a current modern main control panel might look like. Gone are the days where you had knobs and manual switches, but now you've got touchscreen technology and computer technology. Swing arm corner control boxes. With the advent of the swing arm corner, for those of you that may not be familiar with a swing arm corner, that's where the very last tower on the machine will actually extend and retract so that we're not watering in a circle, but we can water in quite the unique shape as necessary. So we're able to incorporate computers in that so that we're controlling the water more accurately that's coming out of that swing arm corner. We're able to control the path of that swing arm corner more accurately, and we're able to do a better job with the irrigation, as well as incorporating computers into remote locations. So let's take a look in detail at some of where those things come into play. First of all, the main control panel. One of the biggest things that we've seen in technology leaps is the ability for automatic operation. Until just a few years ago, when it was time to start your pivot, you got up, you got in a truck, you drove out to the pivot, and you pushed the start button. And when it was time to stop it, you had to go back out there and push the stop button. Now, with the incorporation of PCs, single board computers, programmable logic controllers, we can put in some logic to that so that we can have it start based on time. We can have it start based or stop based on changing field conditions, i.e. weather. We've all laughed at the pivot that's out running in the pouring rain. Well, now we can monitor that. We can take weather data, bring that into this computer, compare values, and have the computer automatically adjust operation. We can record data. What does that computer do? What does that pivot do? How much water are we using? How long is the machine running? Where is the water going? A lot of the things that we're starting to see scrutiny from our natural resources agencies about, we can now automatically record that data rather than having to manually transcribe that data and do calculations. Multiple auxiliary device control. More and more we're seeing with the efficiencies of the devices on center pivots as well as the machines themselves, we're seeing the ability to bring in auxiliary devices, injectables of some type, be it a fertilizer or some kind of a pest control opportunity. We're able to control pump stations, and we're able to control other equipment that might be within the vicinity of the center pivot. So having that PLC control there allows us to automate that and generate reports on what happened. What happened when did the pivot start? When did it stop? How fast was it going? Was its speed changed? Why did it change? Many times we've found an unexpected situation when we return to the field with our center pivots. How come it's there? How come it shut down? How long has it been parked? Was it a safety? Did somebody push the stop button? So now we're able to report that, generate that report, and learn what's going on with our equipment. When our on-farm labor is operating the equipment, we're able to see what happens in real time, and then be able to provide those reports for management operations. As I said, swing arm corners is another opportunity for PCs and PLCs to be used in center pivot applications. Accurately controlling the water during deployment and retraction. This is quite the challenge because we can't just turn on the sprinklers when we are in what's called the partial deployment. When I'm fully retracted, my water is shut off and I'm not irrigating. When I'm fully extended, I'm covering the most ground. But when I'm in that in-between time, what we call that partial deployment, we need to be able to control the flow of water so we're not overwatering those crops in the partial deployment irrigated area. So we're able to do that through the incorporation of PCs that can monitor location, flow rates, valving. It's also programmable for different situations. As we look at multi-crop operations, crop rotations, or changing field conditions, we need to be able to change sometimes what happens with that swing arm corner. So we can program different water application rates for different crops, different soil types, as well as do partial arm deployment rather than either fully extended or fully retracted. We can run that machine with that arm partially deployed. It's given us the opportunity to pick up more acres and be much more effective with the money we've spent out there. Finally, putting computers in remote locations. This would be in your office, in your truck, in your tablet, wherever you might want to coordinate all of your efforts. As we see operations increase in size and number and geography, we need to be able to coordinate that. We're managing more land with fewer resources. So we can use these computers in remote locations through internet access to be able to monitor, control, and operate those center pivots in a variety of different functions. Different manufacturers have different features that they can do, but now from even right here at the show, you can control and operate those center pivots. So doing that with a remote location as well as remotely compiling data, a lot of those log reports we talked about from the main control panel can be brought to a remote location via a communication network we'll talk about in a little bit. So we're compiling information as well, being able to be more effective managers. And finally, desktop programming, laptop programming from wherever you are. You can change, you can adjust your center pivot based on ever-changing conditions in the field. The next topic I want to talk about is GPS guidance and monitoring. What can we do? We can monitor the position of that machine, we can guide our swing arm corners, and we can guide our lateral moves. So with that position monitoring, what we're doing is we're accurately reporting the position of that machine in the field, which will enhance the accuracy of the end gun. We've all gotten a South Carolina car wash when the end gun's spraying out in the highway. Well, now we can accurately control that with a GPS so that we're not wasting water and be effective with that end gun. incorporate the auxiliary control devices as well. So if we're running an injectable, if we're running a pump, we can now incorporate that PLC and that GPS. When the machine is in this area of the field, I'm going to run this auxiliary device. Maybe I only need to inject while I'm in one portion of the field or the other. For swing arm corners, this has given us a tremendous leap forward in effectiveness in operating these machines, because we eliminate that underground guidance equipment, which was a heavily maintenance and expensive maintenance, and it also limited you to that specific path. Now what we can do with the advent of GPS is we can computer enhance that to maximize the coverage area, that swing arm corner, as well as be able to reprogram that for changing field conditions. If you have a wetland in a partial year, or you have some event that occurs under that swing arm corner and you don't want that deployment to happen, then we can quickly change that. We're not stuck with that underground buried wire path. With the lateral moves, this is very similar opportunities. We can maximize the efficiency on that. We've eliminated a lot of that hardware that needs to be maintained for guidance and operation, increasing the accuracy of that travel path. So now we can program auto starts and stops as that machine moves through the field. The biggest benefit is off-tracking and crash potential. Because these are autonomous machines, they're not hooked to a center point. If they off-track from their guidance path, it's very easy to get into a fence row, get into a tree, and can be an expensive opportunity. So now with GPS guidance on this, we reduce that opportunity for off-tracking, we reduce that crash potential, keep that machine operating efficiently. Telemetry is another technology that we've seen. Telemetry is the pathway to get the data from the PCs and PLCs in the machine to your remote PC. And we're seeing 3 different types of telemetry. We're going to explore these in a couple of ways. RF, satellite, and cellular technology. RF telemetry is, RF stands for radio frequency. It's a low-cost, high-volume data transfer. Typically completely owned by the grower, can move a lot of data very quickly. Usually it's capable of being combined with some kind of a remote programming, and it can be used from one machine to another or back to a base station. So you can control one machine from a second, you can daisy chain when I stop, the next one starts, or we can bring all that data back to that central computer at the office. Satellite telemetry is another excellent telemetry product. It's good for machines that are spread over a wide area. With RF technology, we need to get that radio signal to reach that machine. With satellite technology, as long as we've got a clear view of the sky, we have control technology. Doesn't have a base station, doesn't require line of sight, but it is often subscription based. You have to pay to use that data stream off that satellite. Excuse me. As opposed to cellular technology, we're all familiar with the cell phones we carry in our pockets. This is a direct communication from that cell phone to that machine that's located in the field. It is subscription based, but it can be a lower cost subscription, but it does require strong cell service, especially at the center pivot. We find a lot of times these companies, they don't want to spend a lot of money to build cell phone towers where nobody is, and we don't put center pivots in downtown Columbia. So sometimes that can be a challenge using cell phones, but it is an opportunity if you do have a good, strong cellular service in your area. So how do these work with remote monitoring and control? Well, in the RF-based systems, you would combine that with an RF telemetry system and an internet connection at the base station for the radio. That allows you to use that internet connection to connect from your smartphone into your base station and have full functioning operation from your smartphone. It is often a very high level of remote monitoring and remote operation. Whatever you can do at this control panel, you can do from your remote device. However, you do need to make that investment in that RF, and you do have to have an appropriate geography for that RF to operate. Satellite telemetry that we talked about before, it's capable of delivering messages across a wide variety. So we can send messages to a landline phone, to a PC, to a cell phone, or something else. It does require a third party to handle the data, so there can be some lag in delivery time there. And some of the interface platforms that the satellite telemetry networks can use can be difficult to understand. It may not say pivot number 3 is stopped. You may get PVT03STP016. And you've got to know that that means, okay, pivot number 3 is stopped at position 016. So there is some learning curve there, but you've got a much better, you've got a much wider operation. As opposed to cellular, we talked about that being direct. It is relatively low cost installation and service with cell phones. You can put in a cellular modem very easily. You do have to have that strong cell service both at your remote device and at your center pivot so that you can communicate back and forth. The biggest challenge to cell phone telemetry is the ever-changing technology. This is a list of all the different cell phone technologies that are currently deployed today in the world. We see the cell phone companies developing new control technologies every single day. We typically replace our handheld devices every 12 to 24 months. However, a cellular modem and a center pivot may not be on that quick of a rotation schedule for replacement. So if the cell phone company moves to a 4G or maybe a 5G or whatever the next generation is, and you obsolete that communication technology, now you have to go back and update that hardware in your pivot. So those are just some things to be concerned about when you're using those. You do get a high level of functioning with cellular technology, but you do need to keep your equipment up to date with the times. Finally, the last thing I want to touch on is variable rate irrigation. What is it? It's the ability to adjust water as the center pivot moves through the field based on local conditions. Maybe it's a non-crop area, maybe you've got differing soil types, maybe you've got differing crops under the same pivot. So we can use the GPS technology, the computer technology, to program that to say, okay, in this area of the field I want more water and in this area I want less. And as that machine moves through the field, it will automatically adjust. There's two basic types of variable rate irrigation, sector VRI and zone VRI. So what is sector VRI? Sector VRI is the most basic variable rate irrigation, and it effectively speeds up or slows down the machine to change your water application rate based on that machine's position in the field, and it does the whole machine. So you can see in this sample here, we've broken our center pivot circle down into wedges of the pie, and we've given them, in this case, different colors. That's called our prescription, and those colors would represent the desired water application. While that machine is in that sector of the field, it would operate at the appropriate speed to give you the water application you need. Usually this is user programmable with vendor supplied software, very easy to use. In some cases, if you buy a computer control panel, that ability to use this basic level of VRI comes standard with it. As opposed to zone VRI, what we've done here is we've now taken those sectors or those pie wedges and we've split them up in concentric circles going out, and we've put some valving on the machine so that we can also adjust the valves up and on and off to adjust water rates. So you can see our prescription now looks a little bit different because we've got small squares and sectors that we would apply more or less water into those. It does use specific field location. Many times, depending on the manufacturer, you will have to do electroconductivity mapping of your field in order to generate this prescription. Some manufacturers also have a prescription generating software if you don't want to have your field EC mapped. Very high level, this is a more expensive type of variable rate irrigation, but it's much more effective at managing the water. So just to summarize kind of what I have been talking about here, structurally, mechanized irrigation machines haven't changed much, but the developmental advances in remote communication, monitoring, control, water application have made these very technologically advanced machines. And that changing technology gives us increased efficiencies, allows us to reduce our on-farm labor, our operating labor, and get us better reporting. So with that, I've got just a couple of minutes if anybody wants to ask any questions about any of the technology.
Actually, you did very well. So we have about 7 minutes for questions.
Okay.
Go ahead.
Yes, sir.
How difficult is it to update an older pivot?
How difficult is it to update an older center pivot? The salesman answer is that depends. Depends on how old the center pivot is and what technology is on that, what technology you'd like to go to, and whose technology you'd like to use. So if you're going within the same brand, oftentimes it's easier to do. In some cases, if it's already a computer control panel, it's a simple firmware upgrade. If it's an older machine or you want to change brands, then you're looking at changing your main control panel to have the solid state technology if you use an old electromechanical. So depends on how old the machine is. Yeah, it's an easy but expensive upgrade. You simply take the old panel off and you put the new panel on.
How much do those typically, $1,000, $2,000?
Again, depends on where you're at and where you're going. If you've got a computerized control panel from some manufacturers and it's a simple firmware update, many cases that's free. If you're going to have to completely remove a control panel and change your entire operating system, install a GPS, things like that, you could be talking anywhere from $5,000 to $10,000 depending on the manufacturer. Yes, sir.
How are the GPS equipment secured to the pivot or into the control panel?
How is the GPS equipment secured? That's going to be manufacturer specific, but in most cases it's incorporated in the control boxes that are on the top of each tower. So there would be a GPS antenna that would be mounted inside that control box, and then it would be wired through. And most of us use what's called a power line carrier. We'll send the signal back over the power wire to the main control panel, and then there will be a decoder in that control panel. So what you'll get is when you first install that, you'll set up what's called a fixed base. That's where your control panel is. It's not going to move. Once you've stored that location, you put the antenna out on the end of the machine. It compares its position to that fixed location and is able to calculate its distance, speed, things like that. Great. If you've got any more questions or want to talk more specifically about it, feel free to stop by the Rinke booth out here on the show floor, or if you've got a different manufacturer, I know some of the other manufacturers are here. I'm sure they'd be glad to talk about the technology applications they have as well. Thank you very much.
Thank you. All right, before the next speaker, I'd like to remind you that this section we are giving CCA credit for crop management. So if you need CCA credit, please sign this. We have 2 of them for each hour. So if you are staying for each section, if you are staying for each of the 2 sections, please make sure you sign up for both of them.
Remember how that works, right? Ready to go? Yeah, it is. I just didn't use it.
Yeah, it's not on now. But.
Yeah, I turned the switch off. Yeah.
Our next speaker comes to us from BB Hobbs. He has been dealing with drip irrigation for a long time, so I'll allow him to introduce himself.
All right. Good morning. My name is Denman Isgett. I am with BB Hobbs Company and Liberty Acres Fertilizer Corporation. We are a company that sells irrigation and fertilizer. We sell Rinke pivots, and we do drip irrigation. We do traveling guns. And today I'm going to talk to you a little bit about subsurface drip irrigation. Let's see. Step away from that thing. First of all, we're going to get right into it, and this is going to be a broad overview. But what is drip irrigation? What drip irrigation is not is a leak in a hose or a line of water that sprays out. It is a delivery system at or near atmospheric pressure. Reason that is important is it will drip, and I put in parentheses uniform application. Hopefully if a system is designed properly, it will uniformly apply that water over the distance that it is to be applied. We'll cut that off and talk a little louder. This is an example of what the drip should look like when it's operating properly. You notice the water is distributed uniformly, and that's the goal. Why do we want to use drip irrigation? Well, ultimately what we want is we want yield and profitability. How this technology works. Well, drip irrigation, when we're talking specific to drip irrigation, we're talking about a tube that carries water. Within that tube, there is an emission device. In most cases of your higher end drip irrigation, it will be a molded emitter. This is an example of a molded emitter. It would be welded when the extrusion is done on the inside of the tubing or the tape. Water would enter this area, which is called the filter, and travel through this path of jagged teeth, which is called a turbulent path. This is where the energy or the pressure would be burn off as it comes to this area, which is the bath, and that is where the dripper actually drips. A general system layout, you would have your drip irrigation in the field. We'll start with a control station, which would house a pump and a control panel. Your filters would be attached to a main line using a chemigation valve or a check valve. There would be a zone control valve with various vacuum or air relief systems, which is very important. A lot of times if you think you want to see some pipe jump in the ground, don't put air relief in a system. It will move, air will do violent things to pipe. But this is a general layout, and I term this as a short-term system. In this scenario, this field would be replaced in 3 to 5 years, as opposed to what a long-term system would look like, which would be very similar, except here you would have a flush main. The reason that's important, this system would be used for 15 years or more. The reason you have to have a flush main is you have to clean this drip tape, maintain it at a different level. The short-term system would have the drip tape would be tied at the end, some kind of adapter would be placed on it to drain it. Here you would have the design such that a group of tape would be flushed. It would be sized for the pump in the system so that you got velocity and flow to move sediment out of the system. And if at any time you have any questions of any of this, I'm going to go through it real quickly. There's a lot more detail I'm not covering. If you have any questions, please feel free to ask. This is an example of what that flush main would look like at the end of a system. You'd have your drip tape coming into a pipe, which would rise out of the ground. You'd, again, air vents and vacuum relief, a pressure gauge and a valve, and that would be flushed. Each section would be flushed independent of another. And again, it would be done just so that the water movement would scour the inside of the tubing of the tape and remove the sediment. This is an example of an actual design that we did with an existing well, 300 gallons a minute at 40 psi. The blue line represents the main line. So your pumps, your controls, your filtration would be back here. Water would travel through here, and then we have 4 zones, and I've got a closer up view here. You would have individual field valves. So this section would run by itself. It would be its own valve. It would go valve 1 to valve 2 to valve 3 to valve 4, and then it would cycle back to 1, 2, 3, 4. One of the interesting advantages of this system is that you can water all the property, all the field, in a minimal amount of time. In this scenario, a normal run time would be maybe 45 minutes to an hour. We use an hour as a rule of thumb. 4 zones, that's in 4 hours, the entire field has had water applied to it. Then you can start over again. What you're doing is watering a small slice of that soil. So you're going to get to field capacity quicker than you would, say, with overhead irrigation as it travels across. The advantage of that is under high stress conditions, high temperature conditions, you don't limit any spot of the field without water for an extended period of time. A few items I want to address while we're talking about the drip irrigation that you may see that you wouldn't see in overhead irrigation. One would be filtration. This is an example of commonly used filter. It's a disc filter for use in drip irrigation. What it does is it has discs and rings that stack, and water comes in the outside of the filter and goes through. It filters through the discs. This has an automatic backflush mechanism where it would read a differential of pressure in to out at a certain set point. It would trigger a backflush, use fresh water out of the 3 pods to backflush 1 pod, and it would rotate and flush all of these. They also can be flushed on time. Very important. Filtration is very important in these systems. As you can well imagine, when you got a low flow, very small orifices for water to pass, even small sediment can cause tremendous heartache. One of the other components in these systems that is a little unique are the control mechanisms. They can be controlled manually, flip on a valve, flip on a pump. They can be controlled with a simple timer. That's just basically a clock, click on, click off kind of thing. A basic computer where it would be able to cut on and off valves and pumps, including not only irrigation pump, but now a fertilizer pump. And then you can get into advanced controls, and this is an example of an advanced control where you would have data logging of water and irrigation, reading flow meters, having alarms that can understand that a pipe may have burst and I've got a high flow situation. I need to shut the system down. If a valve didn't open in the field, it would recognize that, shut the system down so it does minimal damage. And then, as Mike explained, the technology is very similar where you can tie in to a cell tower or other devices where you can remotely communicate and operate these systems. This is a diagram from Kansas State that they put out, and it's a good illustration. What we're trying to do in these systems normally is use drip irrigation in between every other row to effectively band water to irrigate the crop. In this scenario, and of course we wouldn't have raised beds, but as a diagram, that's what we would try to do, is have a bulb of water that feeds 2 rows. Your traffic pattern would be in between the rows where the drip tape would not be. And this is an example of what it looks like in the field in practice. This is a shallower buried subsurface drip. This tape would be buried 5 to 6 inches deep. And as you can see the droplets. Those droplets the emitters are 24 inches apart. Kind of give you a frame of reference, a distance. And these bulbs of water will wet just like a ball. So what you're seeing on top is deeper as it goes down, and then and soil type would dictate how well it spread and how much it moved. Again, mentioned earlier, one of the biggest advantages to a system like this, when you look at water use by crop, typically you're going to have more water use in the higher stress, hotter temperatures, hotter times of the day. There's not the same amount of water used in the early hours, the late hours as they would be in the heat of the day. With the ability to cycle water across the entire field with a minimal amount, that scenario I gave the example before, those cycles could be 30 minutes. So you could water each block in 30 minutes, so no one area of that field would be without water for 2 hours. So in a high stress environment, high demand situation, you can cycle that water around that field so that you can maintain adequate water from one end of the field to the other for the crop and the crop demand. There are some issues that can develop. This is one of them. It's a good picture. That's the emitter, and that is roots inside that emitter. This often happens when a system is improperly managed. When you have a well-established crop, you get good root growth, and then things turn a little dry. The roots start to go where the most water is. Where the most water is going to be right in that emitter. If a system is run properly and it adequately meets the demand of the crop for water need, this typically will not happen. One of the things about control systems and monitoring and being able to log flows and that kind of thing is when you have the ability to monitor a flow rate per zone, these things, when this starts to occur, you can recognize it quick, and they are treatable. These are things that you can fix if you catch it quick enough. Now some of the installation, I want to show you some of the pictures. This is an example of a sub-main, and here as well, where it's coming out of the sub-main, and this is the buried tubing, drip tubing in this instance. So another example, partially closed sub-main. It's an example of what it looks like with a laying rig. This is a big laying rig. We wouldn't recommend anyone to really lay this much at one time unless the field was level. One of the reasons is that pieces of equipment, especially, you know, they'll tilt, so you may end up with a 6-inch tape here and a 12-inch tape here, and that's going to impact the uniformity in the delivery systems and mechanisms of the system itself. This is an image I don't think is showing up very well. This is a drip tape that is in a shallow bury situation, about 5 inches deep, and kind of give you an idea of what it would look like in practice. That same picture, one of the things, and I don't know whether you can tell it, but right here, you notice a little orange deposit. I don't know whether you can see it, but this water source had iron in it. That's an iron oxide. Untreated, not recognized, those type situations can really cause some problems with these systems. Iron can definitely stop up drip irrigation. Now, knowing that it's there, it can easily be dealt with and quite cost effectively be dealt with. But it's important to know these things are there. Something that you wouldn't necessarily have to worry about with an overhead system. I was going to talk briefly about some of the potential issues that I mentioned before. One of the things that I haven't yet mentioned, insect and pest damage. We have found out the hard way that wireworms will chew on thin mill drip tape. They absolutely love it, will destroy a field of drip tape that's thin. And as a result, we've come to recommend nothing lighter than a 13 mil tape. Anything less than 13 mil tape, you run the risk of wireworm damage. Tubing, anything greater than 13 mil and above, they almost don't impact from what we've seen. Now, in a dry year, rodents, you got water that's running around the perimeter of the field. Rodents and other animals that are looking for water, they will find the water and they will chew on these things. That definitely is a potential problem. These systems, when they're first installed, do require a fair amount of labor. After they're installed, if they're maintained properly, they're not so labor intensive, but the initial install and hookup and evaluation of the system can be labor intensive. It is a little bit of a drawback. I put erosion on here. In a shallow buried drip system, in a field where you have any elevation changes, heavy rains can change the depth of the drip tape by moving some of that soil off site. In areas where a shallow tillage system might want to be used, that can certainly impact the system. If you have an area of field that's prone to erosion and exposes that tape, and then tractor operator doesn't recognize it and runs over that tape, it can certainly be a cause for grief. I mentioned plugging. Plugging is the biggest item, I think, a lot of times that we relate to, and it certainly is one of the things we deal with often. Again, knowing the system, knowing the water quality, knowing the setup, knowing the goals set with the system, most of the time those things can be addressed and addressed quite cost effectively. Depth of placement and soil types can impact the use efficiency of the water that's being applied and effectiveness of the system to grow the crop. In our coastal plain soils, a lot of times we have tremendous variability even in small fields, and that's something that has to be addressed in the system before it goes in. A good design, one thing we look at closely is soil type. And then operational understanding. It is a different management system. You manage the way you water differently. With overhead irrigation, a lot of times you can turn it on and you come back and turn it off or monitor it, and it runs for 8 hours straight. This system will not do that. Or you can do that, but it's not going to be very effective done that way. what you want to do, these systems need to be cycled, they need to be operated. It's not any more labor intensive to operate it, but it is a different management scheme that has to be understood to get the most out of the system. Now the benefits of this system, to me the primary one, especially in our smaller irregularly shaped fields, is you get to irrigate 100% of the field, and you can do so quite uniformly and get a tremendous use efficiency out of the water that you're applying. These systems allow for smaller wells, lower flow rates and lower pressure, lower energy inputs to cover more area. And the field, as I mentioned before, minimal time between irrigations or areas of the field that see water. And I don't think that can be understated a lot of times in a field, especially bigger fields or oddly shaped fields, even with a traveling gun, how much time somebody has to get up, turn the gun around or position the gun, pull it out, pull the reel out, how long it takes a pivot to walk across the field. In this scenario, you're getting water on a regular basis across 100% of the field, which is an advantage. Improved crop uniformity and yield uniformity, I think, is often understated. To get fertilizer and water as efficiently to a corner of a field as you do in the middle of the field, with these systems, a good design will do that. It is a fertilizer delivery system, and this past year, we were talking earlier, in this past year when it was wet and you couldn't get a piece of equipment in the field to spread fertilizer, this system could have uniformly applied fertilizer from corner to corner of the field without having to run an implement in the field. Obviously, we like fertigation, and we think you can get a tremendous gain with use efficiency of the fertilizer applied by using this system as a fertilizer delivery system as well. Fertilizer and nutrients can be matched to the need of the crop, not only in totality, but also at the growth stage of the crop. And then there are certain other management benefits, especially when you go to automated controls and how the controllers are used. It can be a monitored system instead of an operated system. They can be quite cost effective. And again, I mentioned fits irregular shaped fields. They can be designed to fit any kind of field and irrigate and fertilize from corner of corner. I don't know whether you're familiar with the 4R technique, but right source, right rate, right timing, right placement. These things are really, when you get down to the detail of being able to distribute all of the plant nutrients, all of the water requirements specific to the crop stage of growth and the need at the time. You got ultimate control of the irrigation, and using fertigation, ultimate control of the fertilizer. Even if you're zoning, we talked about that one example had 4 zones. You could treat zone 1 differently than 2, than 3, than 4 if you have different soil types, added nutrition, more potassium, less potassium. You could do all kinds of different things. You have a lot more control over the application. And ultimately the goal is higher yields and higher profit. And ultimately you want to be able to make more yield. And with that, that's pretty much all I had. Anybody has any questions? Go ahead, Walt.
What's the greatest depth you've seen based on the soil type that y'all have been able to?
What is the greatest depth of being able to lay the tape? We've had some fields where it's 14 to 16 inches and performed well, but it's the continuity of the soil from the soil surface to that depth that's important. It really depends on soil type, but there are soils in South Carolina that we can go 14, 16 inches depth without any problem. Most of the soils, and I typically say as a rule of thumb, 5 to 6 inches is ideal. Sometimes we can go to 8, sometimes we go to 10, but it really depends on the soil type. Yes, sir.
What about the slope of the field? You've got a lot of some fields that's kind of got some rolls to them. How would that work?
When we design the system, the topography is taken into account, and that design you saw was generated by a program called Irrigation. And it's what it can do is analyze that system, row to row, dripper to dripper, and we put the topography in there, flow rates, pressures, pipe sizes, all those things, air vents, all those things are engineered such that they maximize the use of everything. And we can actually identify where the pressure changes and water changes will be in those systems. So the type of tape used, the type of emitter used, the placement, the layout, all those things will be taken into account to give you the efficiency. And we designed for about a 90% minimal efficiency of the system. So the last emitter in the far corner of the field will be no less than 10% different than the center of the field. Yes, sir.
What are people doing about compaction? I know with guidance, I guess you could try to straddle the rows of the subsoil, but are people doing that with success?
And I didn't address that probably as effectively as I should. One of the things that is essential with these systems is good GPS guidance equipment. When the tape goes in, to mark it, to know exactly where it is. As long as that's done and you have good equipment, we have folks that are subsoiling, because we're doing every other row, and if you have that established and you trust a guy on the tractor to read it and operate the system correctly, then it should not be a problem. The only asterisk to place to that is at the end of the field, there will be a submain. Somebody has to be cognizant of that. In the design I showed, we had the submain in the middle of the field because of the length of run was such that it was most efficient to do that. Now, you might want to make that a grass strip. If you have the GPS equipment, a guy on the tractor knows where to pick it up and go across and then come back down. Those kind of things. It definitely has to be operated and managed differently, but you can certainly still subsoil and do things with the precision technology we have today with equipment. And also the shallow buried tape, you can still use some of the shallow buried tillage equipment and actually till the soil with that tape. Again, quality driver, quality equipment, but it can be done.
And are you limited anyway on, say, length of run? I mean, you pretty much work it out on any size field?
Any size field, any dimension. Now you might have to break it up, might have to be broken up differently, different lengths to maximize that efficiency. All those things go into play when it comes to look at efficiency of the system and how it is. But absolutely, what we typically do is we'd take a field. If you had a field you were interested in, we'd take that field and our designers would import it into AutoCAD. They digitize it, put it in this Irrigation program, and then they would begin to lay in these mains, sub-mains, figure on pressures, elevations, and all those things to maximize both the cost of the infrastructure to put the system in and the uniformity of the system, the performance and the long-term performance, hopefully, of the system. Yes, sir.
A lot of row spacing. I mean,
It can be,
maybe it's going to cost more, I guess, if you're on there. I mean, how do you figure that up for 40-inch spacing versus?
yeah, if you're on 30-inch spacings or 38s, you're going to have more tape or more tubing on a 30 than a 38.
You're stuck with that in that field. I mean, you're stuck with planting that same spacing.
You're stuck with planting that same spacing. Now, one of the things like I talked about, that short-term versus long-term scenario, I think there could be some applications depending on your rotation where you could cost-effectively irrigate for 3 to 5 years, depending on your rotation and your crop, depending on the field. But wheat, we got fields that are rotated into wheat. Now, one thing you won't get with wheat, is you're localized in a smaller area. But typically on a wheat crop, we don't have as much dry weather conditions. It's not as impacted quite as much, and we have seen some effective irrigation with these systems with wheat. But if it did turn dry and you did have to use that irrigation, you'd probably see some up and down. Yes, sir.
Do you need, y'all found the need to subsoil?
In some situations, yes. In some situations, it hasn't impacted the ability of the crop to produce maximum yield. Again, soil type related, equipment related, management systems related. We've had some growers that put these systems in with the intention not to subsoil and found they needed to, and vice versa. It's, you know, it's older technology. The technology's been available for a long time. We've used this technology for, 30 years or more in the vegetable industry, high commercial vegetable, high value crops. This is a new application to it, and we are learning, and the variability of our southeastern soils creates more learning opportunities, let's say. but we're learning.
One of the things that you didn't cover was the $1 million question is how much does it cost?
How much does it cost?
Yeah, and I know that's a difficult question to answer because it depends. If we have, let's say, 100 acres.
Well, let's just say that example you showed, 4 zones, 60 acres.
Let's see.
Make it fair with the
Well,
pivot.
well, probably.
The same question.
And
It costs to install a pivot in the 100-acre field versus this.
well, in the salesman answer, like Mike said, it depends.
Yeah, it depends.
But what we can do, and we sell Rinky pivots. So what we can do, and what we do often, is you take that field, we could compare that field with a pivot and drip. Some fields we do pivots, and then we catch the corners where the pivots don't hit with drip on the same system. That all these things are available and viable options. Typically speaking, depending on the field, with a reasonably square field like we showed there, most of the time the drip system and the pivot system are going to be comparable in price. That's better to say. Now, if you had a small field that's very long and narrow, that kind of thing, then the drip may have a price advantage. If the field is more round and the size of the field, if you have a uniform 200-acre field, then the pivot's probably going to be a fair amount cheaper than the drip. So it all depends. It all depends. But in general, in most of our fields, it's going to be close. Any other questions?
These fields that you were saying, you have a pivot and then you're catching the corners with the drip. Is that pulling off the same well?
Same well, same system. You can valve it so that you separate it, and those things can be engineered. It can be engineered to do it.
You're say pumping 1,000 gallons a minute
Yes.
or whatever. You have to do a VFD, or you can do it.
You can do it multiple ways. You can do a VFD. You can do multiple ways. There are multiple options to do that. You can run them. For instance, you can design the system to run them at the same time, with pressure reducing valves and things in the field to limit the pressure that the drip sees, but maximize the use on the overhead. There are ways to do it. Any other questions? Thank y'all.
Thank you to the speaker.